Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help get you started on number 39 in chapter 13 in your OER University Physics textbook here. So it says, what is the orbital radius of an Earth satellite having a period of 1 hour? Well, the first thing you want to do with any of these problems is draw a picture that kind of describes it here. So we've got some sort of satellite here, and it is going around the Earth. So I got a picture of the Earth here. The orbital radius would be the distance from the center of the Earth to the location of the orbit. So this is what they're asking for right here. So the first step in all of these problems is always to draw a good picture of the problem. The old saying that a picture is worth 1,000 words. In physics, I like to say it's worth 2,000 words. So draw a good picture that describes the problem. So here's the Earth. I've drawn in the orbital radius. Here's kind of a little picture of my satellite here. At the instant shown, it's got a velocity that would point, this way, tangent to the curve here. If I drew it right here, the velocity would basically be like into the screen. Right here, the velocity would point right and so forth. Now, after your picture, you have to decide on a method to analyze this problem. Now remember, in physics, at least if you're in my physics class, at this point in the class we've talked about three primary ways to analyze problems. One, the study of motion, right, kinematics, where typically we draw velocity or maybe speed graphs and talk about slope and area and how to use those concepts to write equations. Second, Newton's second law, F equals ma. Keep it in mind, this is a vector law. Third, principles of work and energy. The overwhelming majority of the problems in any first semester college physics or engineering physics class, the problems are almost always going to result in at least one of these methods. So we have to choose one. Now, let's talk about this guy right here, work and energy. As this thing goes around, it doesn't say anything about changes in height. So I'm going to infer that this is a reasonably constant distance in this problem, and that means that the potential energies are constant or close to it, and that means constant kinetic energies, and there's no external force acting on this system here. So this is just not a work energy problem. If you try to write out a work energy equation for this, you're going to end up with equal potential energies, equal kinetic energies, and it'll just simplify to 0 equals 0, which is nice, right? That's a nice true statement here, but it's not going to help us solve the problem. So it's got to be one of these two methods. So start with a free body diagram of the satellite here. There should be one force, right? The gravitational force, which in general, by Newton's theory of gravity, can be written like this, where the big M here is for the mass of the Earth, the little m, the mass of the satellite here. So I'll put little m, big M. You can also just write it M1, M2, or mass A or mass B. That doesn't matter. The R here is going to be this radius of curvature. Now, that's going to be the only force acting on this satellite. So next is you apply Newton's second law, right? Which is net force equals mass times acceleration. Remember, these are vector quantities. So for the net force, you're going to use this expression. For the acceleration, you have to recognize that's a centripetal acceleration. So there's a very specific way centripetal acceleration is calculated. Out of this, you're going to get an equation here, but it's going to have two unknowns. You're not going to know the speed, and you're not going to have the r. So because it's going to have two unknowns, you're going to need another equation. The other equation will come from a motion analysis. If you do a quick graph of speed against time, so magnitude of the velocity against time, when you're talking about circular motion problems, I find that speed graphs, they're just more convenient to talk about than velocity graphs, because technically, the velocity, you define a direction, and this thing's direction is constantly changing. But this is a constant speed problem, which means this graph is going to look horizontal out to any time I'll just call t here. Now, if for t we use the orbital period, which is given in the problem, 1 hour or 3,600 seconds, then the distance traveled would be exactly one revolution. So the distance would be 2 pi r. So you just have to figure out how to use this graph to put this stuff together. And remember that the distance traveled is going to be the area under that curve there. So what will happen is you'll get a second equation out of this that you can combine over here and solve for the radius. Part B, where it says something about what is unreasonable about this result. I haven't worked it, but I suspect what's going to happen is you're going to get a very, very, very small radius here. Or maybe a very big one, I don't know, but very likely small. And if that radius here puts you within the influence of the Earth's atmosphere or less than the radius of the Earth here, then it'd be completely unreasonable for sure. But they're just asking you to comment on that. So after you calculate the radius, go back to this picture and see roughly where it puts you. You know, if you get something like this, I'd say there's nothing unreasonable about it. But if you get something like maybe this, where it's inside of the Earth, then you've got an issue with the math. I'm sorry, no issue with the math, but your calculated radius would be too small for reality because the thing cannot orbit inside the Earth. So that should be enough to get this problem done. Again, attack it from first principles. Free bodies, Newton's second law, and a study of the motion of the satellite. All right? Enjoy.